So if we look at the difference between graph 7 and 8, these have the same order. They both have 6 vertices, have the same size, they both have 6 edges, and they have the same degree sequence. Every vertex here has degree 2, but they're clearly different. So what is the difference between them? How would you express that? Graph 7 is connected, whereas graph 8 is not. That's absolutely right. We can think of connected as like a 1-0 property where the answer is either yes or no. Or you could also say they have a different number of connected components, and there the answer can be any positive integer. Either of these is equally valid. So those are some easy ones that we can use to flesh out. Those are some easy properties that we can use to flesh out and determine that two graphs are not isomorphic. What about graph 9 versus graph 10? So I believe that these have the same order, same size, and the same degree sequence. So, but I don't think they're isomorphic, do you? You see a way that we can determine that they're not? These two graphs are not isomorphic? The distance is the length of the shortest path between two vertices. So in this graph, I can look at my two vertices of degree 1, and I'm going to label them A and B just for simplicity's sake. And there are two paths from A to B. There's one here that goes 1, 2, 3, 4, 5 edges, and another here that goes 1, 2, 3, 4, 5 edges. So the distance from A to B in this graph is 5. So when we say the length of the path, we mean the number of edges. The minimum number of edges you would need to cross to get from one vertex to another. Now if I think about this, and I think about this A and this B that I've labeled, each of these is a vertex of degree 1. So if I had an isomorphism, if we had an isomorphism alpha and A, alpha of A and alpha of B would have to be vertices of degree 1, because isomorphism is going to preserve degree of individual vertices. Well, I have two vertices of degree 1 in this graph, but the distance between these two is 1, 2, 3, 4. However, the two vertices of degree 1 in graph 10 have a distance of 4. So here's my argument as to why no isomorphism is possible. And the structural property that I'm going to rely on here is the distance between vertices. First, I'm using degree to say, well, let's look at the distance between the degree 1 vertices, and in the two graphs, so they can't be isomorphic. What about graph 11 and graph 12? Here we're going to have 3 vertices of degree 1 in graph 11. Graph 12 also has 3 vertices of degree 1. So let's look at the pairs of distances, or let's look at the distances between these pairs of vertices. So I have 3 choose 2 distances. The first distance will be 1, 2, 3, 4. These are not necessarily in any order. Second is 1, 2, 3, and the third is 1, 2, 3. So if I look at the pairs of degree 1 vertices, there's one pair that has distance 4 between them, and 2 pairs that have distance 3 between them. Now if I look at this other one, I again have 3 vertices of degree 1, so there will be 3 pairwise distances, but one of these distances is 2, one of these distances is 4, and one of these distances is 4. So there are 2 pairs have distance 4, and one pair has distance 2. So these can't be the same. These can't be isomorphic, because if I look at a pair, a distance 3 pair here, it would have to map to a distance 3 pair. So these become more and more subtle as you go along. And this is a problem that people have worked on for about 50 years at this point, and we don't have a fast algorithm that in general will give you a decision about whether or not there's an isomorphism. So it's not possible to take this property and reduce it to a bunch of yes, no, or easy to calculate numerical questions. If you're doing it by hand, these are the types of things you can try to do logically. But in general, for large graphs, it's a hard problem, and there's no way around that.